In the last lesson, we talked about harmonic waves and also discussed how two harmonic waves interfering at a point can be a constructive interference producing a bigger wave or a destructive interference producing no wave. That concept we will use today to build a new concept of harmonic stationary waves. Now, what are stationary waves? The word stationary suggests that it's not moving. Is that right? Stationary waves. Can a wave be stationary? Well, first of all, let's look at the direction of displacements of particles as the wave advances in a medium. Now remember, the profile of a wave is created by the phase of vibration of each particle, because each particle in the medium is going to be in a different phase of vibration. As the energy of the wave passes through the medium, we get the profile of a wave. Now, if you look at a wave on a crest and a trough, if a particle is on the crest of a wave, tell me, what is the direction of motion of that particle? A particle on the crest of a wave has actually reached the peak and now it is beginning to move down. So this particle is now beginning to move down. How about a particle on a trough? A particle on a trough has reached the lowest possible point in its displacement and is now beginning to move up. That means the direction of motion of a particle on a crest is opposite to the direction of motion of particle on a trough. Therefore, what will happen? What will be the state of vibration of a particle which is subjected to the crest of one wave and the trough of the other wave? We talked about this in the last class. If this particle is on the crest of one wave and the trough of the other wave at the same time, that means wave 1 will want this particle to move down, wave 2 will want this particle to move up. What will this particle do? Well, it will not move. It will stay at the equilibrium position. There you go. So here we have a particle here which is supposed to be on the crest of the red wave and the trough of the green wave. What will that particle do? Well, it will have no displacement. The displacement produced by the green wave will be cancelled by the displacement produced by the red wave. The particle will stay at rest. Well, so the result of such a superposition is what we call destructive interference. Now, stationary waves are actually formed by the constructive and destructive interferences of two waves advancing in the opposite directions. We will have a look at that as we go on. If the particle is on the crest of both the waves, then the displacements will add up and superposition will be constructive. So when there is constructive interference, the displacements of the particles will be maximum, and when there is destructive interference, the displacements of the particles will be zero. Now, this is an example of constructive interference. The particle is the red wave and the green wave produces displacements in the same direction. Therefore, the total displacement will be the sum of the two. You got a bigger wave. A constructive interference results in a bigger amplitude wave. You can see a bigger wave means a bigger amplitude. a destructive interference will result in no wave at all. So two waves meeting at a point can interfere constructively or destructively, producing a bigger wave or sometimes no wave at all. Now we are going to now use this concept to construct the concept of stationary waves. Now this is a mechanical vibrator. This vibrator can be made to move up and down, producing a vibration on the string that is attached to it. You can see a length of string is stretched between the vibrator and the pulley, and I have used a weight to stretch the string, in other words, to produce the tension. Now listen carefully here. When the vibrator vibrates, a disturbance is created. Now the disturbance advances along the string, and when it reaches the pulley, it gets reflected. That means the energy gets reflected and it comes back here. Now by the time the energy comes back, if the vibrator is ready for a fresh vibration, the two energies will add up. In other words, the energy of the returning wave and the energy that is produced by the new vibration are in phase. You see that? Now that will produce a bigger wave. So what is the criteria for that? The criteria is, by the time this particle completes one vibration and ready for the next vibration, during that time the wave produced by the first vibration must go and come back. Then these two will be in phase. Well, a mechanical driver attached to one end of a stretched string sets that end into up and down vibrations, sending wave pulses down the length of the string. Now these wave pulses get reflected at the pulley. That means you have an advancing wave and a reflected wave. Now what happens as the advancing wave and the reflected wave interfere? Don't they interfere? Well, each segment is now subjected to the advancing wave and the reflected wave. Now how will the vibrations of each particle be affected because of that superposition? Each particle on the string is subjected to displacements due to the advancing and reflected wave. Alright, let's now talk more. Now the green wave is the advancing wave. Here is the advancing wave, and the red wave is the reflected wave. So you must understand that the green wave is moving to the right and the red wave is moving to the left. Now let me see if I can construct that on a very clumsy model here. Now this is the green wave, and I could not find the red one, so I'm using a white one here. Now the advancing wave and the reflected wave. So the green wave is going to go to the right, the white wave is going to go to the left. And you can see at some time, look at this, how they superimpose. You can imagine at a particular time the crest of the green wave and the crest of the white wave are together. That means a particle here will have maximum displacement. The trough of the two waves are together. The particle here will have maximum displacement. Now watch. The direction of motion of the green wave is to the right. Is that right? Now watch me do that. The green goes to the right, the white goes to the left, and as a result, what is happening now? Now the crest of the white wave falls on the trough of the green wave a little later. You see? So as the waves advance, Now they are in phase. So the advancing wave and the reflected wave meeting at a point with the crest of the advancing wave on the crest of the reflected wave, the trough of the advancing wave on the trough of the reflecting wave. What will happen? The instant when the crest and trough of both waves coincide, the string segments have maximum displacements. Everywhere on the string, the particles will have maximum displacements because both these waves are meeting in phase everywhere. So the string segments will have maximum displacements. But this only stays for a fraction of a second. Why? Because the green wave is advancing to the right and my white wave is advancing to the left. Now you can see they are now in phase. Now the green wave advances, the white wave also advances. What is the situation now? Now the trough, the crest of the white wave is on the trough of the green wave. That means what will be the state of vibration of particles then? Now this situation happens only for an instant because the waves are advancing in the opposite directions. Soon the crest of the advancing wave will fall on the trough of the reflected wave. The green wave is the advancing wave, the red wave is the reflected wave. Now look what happens. Now particles, particularly here where the crest of the green wave and the trough of the red wave fall, that particle will have no displacement. That means the particles all over here will have no displacements. Since all the segments now are subjected to opposite displacements, they will remain stationary. That means none of the segments will have any displacements when the situation is like this. But this again will stay only for a fraction of a second. Now this process will repeat. Why does it repeat? Because one wave is advancing to the right, the green wave is advancing to the right, the white wave is advancing to the left. Now watch once again. Now can you see they are in phase? As they move, they become out of phase. There you are, they are out of phase. And now they are in phase, and so on. So alternatively, they come in phase and out of phase continuously. And what is the result? When the string segments, when the advancing wave and the reflected waves are in phase, the string segments have maximum displacement, and this is what you see. Now some points on the string will be permanently at rest. You see, a point here will be at rest all the time. They will not have any displacements at all. And some particles will have maximum displacements, minimum displacements, maximum displacements, minimum displacements. It will appear and disappear. And that is the reason why we call it stationary waves. You see, although stationary waves are caused by an advancing wave and a reflected wave, what you will see on the string are the string particles will have maximum displacements, minimum displacements, maximum displacements, minimum displacements. They appear and disappear. In other words, the wave seems as though it is not advancing. Some points on the string will be permanently at rest. For example, this string has 1, 2, 3 points which are permanently at rest. And such points are called nodal points. And we will represent them by N. This is a nodal point. this is a nodal point and this is a nodal point. Points where the string segments have maximum displacements. If you notice, this is a point where the string segments will have maximum displacements. Now such points are called antinodes. We will represent that by the uppercase A. This is an antinode, this is an antinode. Now, you can see this mode, the process of maximum and minimum displacements appearing and disappearing is called the formation of stationary waves. So the process of forming stationary waves on a stretched string is due to the formation of maximum and minimum displacements appearing and disappearing due to the interference of the advancing and the reflected wave. Alright? Okay. Now, the wavelength of a stationary wave. You know, in the last lesson we talked about the wavelength. Now, you know that wavelength of a wave contains a full crest and a full trough. You see that? A full crest and a full trough. So, in the case of a stationary wave, you know, a stationary wave produces segments. You notice that this is a segment. The distance between two consecutive nodes can be considered to be a segment. So how many segments are here now? 2 segments. Now the wavelength of a stationary wave is the length of 2 segments. The distance between 2 alternate nodes, not the distance between 2 nearest nodes. The distance between 2 alternate nodes is the wavelength of a stationary wave. Alright. Now, therefore, the distance between 2 adjacent nodes will be half of a wavelength. The distance between 2 adjacent antinodes will also be half of a wavelength. So, wavelength is the length of 2 full loops. A segment is a loop. Is that right? It's better to call it a segment rather than a loop. The number of nodes and antinodes on the string depends on the frequency of vibration of the string. Now you remember I told you that by the time the vibrator completes one vibration, if the wave goes and comes back, then the string will vibrate in one segment. But suppose by the time the energy goes and comes back, if the vibrator completes 2 vibrations, then the string will vibrate in 2 segments. Now, by the time the energy goes and comes back, if the vibrator does 3 vibrations, then the string will vibrate in 3 segments. That means the number of segments that are produced in a stationary wave depends on the frequency of vibration of the vibrator. Well, I think I'm going to demonstrate that to you. I will show that to you in a demonstration a little later. Alright, let's see if I can demonstrate that to you. I have now a string stretched between the mechanical vibrator and the fixed end. You can see the string vibrating. The mechanical vibrator vibrates up and down. Now, if I can adjust the frequency of the vibrator such that by the time it completes one vibration, the energy goes to this end and comes back, then this string will vibrate in one loop. Let me see if I can do that for you. I'm going to increase the frequency and, well, do you see the string vibrating in one loop now? There is one segment. That means you have, look at the antinode. where I'm pointing is the antinode. This is the node and this is the node. Now at this time, when the vibrator completes one complete vibration, the energy goes to the end and comes back. The new energy of the vibration now get reinforced with the reflected, and you can see there is constructive interference here. Now I'm going to double the frequency of the mechanical vibrator, see what happens. Alright, that is our one loop. Now I'm increasing the frequency. You notice that the segments have disappeared. Alright, let's increase the frequency. What is happening now? The string is beginning to vibrate now in 2 segments. Now notice this beautiful 2-segment vibration. Now that means by the time the vibrator completes 2 vibrations, the energy goes and comes. You can see there is a node here, an antinode here, a node here, an antinode here. Okay, if I make the frequency of this 3 times the original frequency, what will happen? I'm going to make the frequency 3 times and see what happens now. Alright, now the frequency of the mechanical vibrator now is 3 times the original frequency, and you have 3 full segments. You can see a node, a node, a node, a node, an antinode. Alright, I touched it. Antinode, antinode, antinode. Now, what is the wavelength of this wave? If you want to measure the wavelength, you need to measure it from one node to the alternate, to here. That will be a wavelength. The length of one segment will be half of a wavelength. Okay, I'm going to now increase the frequency to 4 times the original value. Alright, see what happens now. There you are. The string is now vibrating in 4 segments. Isn't that beautiful? So how many nodes are there? There is 1, 2, 3, 4, 5 nodes. How many antinodes are there? There's 1, 2, 3, 4 antinodes. Now these are stationary waves. I hope you enjoy watching these stationary waves. Alright? Now watch this computer animation of a stationary wave. Advancing wave gets reflected. The advancing wave and the reflected wave now interfere, producing the stationary wave. Now this is how stationary waves are formed. This is the case of 1 segment vibration. In other words, the frequency of the vibrating object is such that by the time the energy advances and returns, it completes 1 vibration. And now, if you double the frequency, you will get 2 segments vibration. There you have the 2 segments vibration. You have 3 segments vibration, and so on. Well, you have now got a clear picture of stationary waves. Now, what is the simplest mode of vibration of a string that is stretched between 2 points? The simplest mode of vibration is that you have nodes at the fixed end and an antinode at the middle. Is that right? It will look like this. This is the simplest mode of vibration, with a node here, an antinode here, and a node there. And what is the length of the string in relation to the wavelength at that time? Can you tell me? This is the complete length of the string. The complete length of the string now contains how many wavelengths? The distance between 2 adjacent nodes is half of a wavelength. Is that right? Now, the frequency of the string vibrating like this is called the fundamental frequency of the string. So, when the string vibrates in one segment, the frequency of vibration is the fundamental frequency. Okay? For the fundamental mode, the length of the string contains half a wavelength. That means this length from here to here will be half of a wavelength. We will say the length L of the string equal to lambda by 2, or the wavelength of that stationary wave will be 2 times the length of the string. So the length of the string now contains half a wavelength, or the wavelength will be 2 times the length of the string. Now, what is therefore the frequency of the fundamental mode? Now remember that wave equation. What is our wave equation? Do you remember? The equation that connects the wave speed, frequency and wavelength. V equal to F lambda. Therefore, F equal to V over lambda. Now, I'm going to call the frequency of the fundamental mode as F1. So, F1 equal to V over lambda, and for the fundamental mode, lambda equal to 2L, and therefore, this is the frequency of the fundamental mode of vibration. F1 equal to V over 2L. Alright, don't forget this. This is the frequency of the fundamental mode of vibration. What is the next higher mode of vibration? When you double the frequency, the string begins to vibrate in 2 segments. And so, the next higher mode of vibration is this. The string vibrates in 2 segments. That means there is a node there, a node here, and a node at the other end. There are 3 nodes. And how many antinodes? 2 antinodes. This is the second mode of vibration. The frequency of this is twice the fundamental and is called the second harmonic. The string is now vibrating at twice the fundamental frequency, and twice the fundamental frequency is called the second harmonic. For the second harmonic, what is the relation between the length of the string and the wavelength? You can now see the full length of the string contains 2 full segments. That means it contains a full wavelength. Is that right? Yes. The distance between 2 alternate nodes is now a wavelength. So the length of the string now contains a full wavelength. So the wavelength of this mode is lambda equal to L. Therefore, you can see, therefore, what is the frequency of the second harmonic? Well, F equal to V over lambda, is that right? I'm going to call the frequency of the second harmonic as F2 equal to V over lambda. And what is lambda equal to for the second harmonic? Lambda equal to L. So that will be V over L. And I can write this as 2 times V over 2L. Why did I write like this? Because V over 2L, if you remember, is the frequency of the fundamental. So the frequency of the second harmonic is 2 times the frequency of the fundamental. It is 2 times F1. The second harmonic is twice the fundamental. Now what is the next higher mode? In the next higher mode, the string will vibrate in 3 segments. Now look at these segments. This is the third mode of vibration. You have a node there, a node, a node, a node. There are 4 nodes. And how many antinodes? An antinode, an antinode, an antinode. The frequency of this is 3 times the fundamental, and you call it the third harmonic. So the fundamental, twice the fundamental is the second harmonic, 3 times the fundamental is the third harmonic. Now for the third harmonic, the length of the string contains, now if you notice, this is the total length of the string. The total length of the string contains now how many waves? Now, one full wave is a distance between 2 alternate nodes. That is one full wave, and this is a half wave. So, the length of the string now contains a full wave and a half wave. In other words, it contains 3/2 wavelengths. That means lambda equal to 2/3 of the length. If this is the length of the string, wavelength is this, which is 2/3 of the length of the string. Alright, so what is the equation for the frequency of the third harmonic? F3 equal to V over lambda, and lambda equal to 2/3 of L. So replace lambda by 2/3 of L. Now, this can be written as 3 will go up, is that right? That will be 3 times V over 2L. I hope you understand that. And what is V over 2L? V over 2L is the frequency of the fundamental. So that will be 3 times F1. The frequency of the third harmonic is 3 times the fundamental. Now, I have the diagrams illustrating many more modes of vibration. Look at this. The fundamental mode of vibration, the frequency is 1V over 2L. The second harmonic, the frequency is 2 times V over 2L, 2 times the fundamental. The third harmonic, the string vibrates in 3 segments. The frequency is 3 times the fundamental. The fourth harmonic, the string vibrates in 4 segments. The frequency is 4 times the fundamental. Fifth harmonic, the frequency is 5 times the fundamental, and so on. Alright. Let's now talk about quality or timbre of a musical note. Now, do you know that a guitar is actually a stretched string? When you pluck it, the guitar wire will vibrate, and it can vibrate giving out its fundamental frequency, the second harmonic, the third harmonic, and so on. But most of the time, when you pluck a guitar wire, it will be vibrating in its fundamental mode, that will be in one loop. But along with the fundamental, the string can also vibrate in higher harmonics. And it is this phenomenon that contributes to the quality of a musical note. Now, what is the meaning of quality of a musical note? When the stretched wire of a piano or guitar, piano is also using stretched wire to produce the musical note. It vibrates with notes at fixed end and antinodes at the center, emitting its fundamental frequency. The sound you hear when you strike a piano key is actually the fundamental frequency of one of the wires. If you open up a piano, you actually will see a large number of strings. Each string has a particular length, and you know the length will determine the frequency, the fundamental frequency. Remember, the fundamental frequency is V over 2L. So if you change the length of the string, the fundamental frequency of vibration will change. So this is the basic or fundamental mode of vibration of a guitar wire or a piano wire. Now, along with the string vibrating in this fundamental mode, a string can also vibrate in higher harmonics. In other words, the higher harmonics are very often superimposed on the fundamental. So the sound you hear is not only the frequency of the fundamental, but a combination of the fundamental and the higher harmonics. Now, it is this combination of the higher harmonics with the fundamental that gives a musical note its quality. And the quality of the musical note can be used to distinguish between a note that comes from a piano, or a note that comes from a guitar, or a note that comes from a drum, or a note that comes from a piccolo, or a note that comes from a flute. You see that? They are all musical instruments. A particular note means a particular frequency. Although all these musical instruments can produce the same frequency, they will all sound different. It is that difference we call timbre or quality. And what is the contributing factor for the timbre of a musical note? It is, along with the fundamental, the vibration can also be in the higher harmonics. It is the combination of the higher harmonics. In different musical instruments, the combinations of the higher harmonics will be different. And that difference in the combinations of the higher harmonics produces that particular timbre of the sound that comes from a particular musical instrument. All right? Let's now obtain a wave function for a stationary wave. A stationary wave function. Now, do you remember how stationary waves are formed? Stationary waves are formed when an advancing wave and the reflected wave superimpose on each other, and the resultant wave is the stationary wave. Standing waves are formed by the superposition of two homogeneous waves. What does that mean, homogeneous? They are identical in amplitude, frequency, and wavelength, because it is the same wave, advancing wave and the reflected wave. The same wave gets reflected. They are basically the same wave. They are homogeneous. But one is advancing to the right and the other is advancing to the left. Let me ask you. In the last lesson, we developed equations for a harmonic wave advancing to the right and a harmonic wave advancing to the left. Do you remember those equations? Well, y equal to a sine kx minus omega t is the equation of the wave that advances to the right. Y equal to a sine kx plus omega t is the equation of the wave that advances to the left. So a wave function for a wave advancing to the right is y1 equal to a sine kx minus omega t. And a wave function for a wave that advances to the left will be y2 equal to a sine kx plus omega t. And these two waves now superimpose each other. That means the resultant displacement at any segment of the string will be y1 plus y2. Alright, what is y1 plus y2 equal to? Now remember, in this case, k. K is called the, what's the name for k? I told you not to confuse it with the spring constant. It is not a spring constant. It is just the wave number given by k equal to 2 pi by lambda, and omega is called the angular frequency, which is 2 pi f. Now the sum of these two waves is y equal to y1 plus y2, a sine kx minus omega t plus A sine kx plus omega t. Now, can you use the equation I gave you in the last class? Sine of A plus sine of B, and expand this? Well, we can expand this using the trigonometric identity we used in the last class. Sine of A plus sine of B is 2 cos A minus B divided by 2, or 1/2 A minus B, times sine of 1/2 A plus B. Our A is kx minus omega t, B is kx plus omega t. So that will be, when you add them, you get 2A, this A will be common that comes out, that will be 2A cos omega t sine kx. Is that right? If you subtract kx minus omega t minus kx minus omega t, will be negative omega t. Is that right? 1/2 of negative 2 omega t will be negative omega t. And cos of negative omega t is cos omega t. So the resultant wave is y equal to 2a cos omega t sine kx. And this is the equation for a stationary wave. So the equation for a stationary wave is yxt equal to 2a cos omega t sine kx. Okay. Let's now talk about the laws of transverse vibrations of a string. What are some of the fundamental laws that governs the transverse vibrations of a string? What is the meaning of transverse vibrations? The string segments will be vibrating up and down. The wave will be advancing at right angles to it. Well, the speed of transverse waves on a stretched string, do you remember that equation? We obtained that on the first lesson on waves. What is the speed of transverse waves on a stretched string? Is V equal to square root of T over mu, where T is the tension and mu is the mass per unit length, called the linear density. Well, you know, T is the tension, and of course mu is the mass per unit length. But you know that V, the wave speed, equal to frequency times the wavelength. So let's replace V by F lambda. We get F lambda equal to square root of T over mu. And now let's solve it for F. Therefore, F equal to 1 over lambda square root T over mu. Now, this gives us the frequency of vibration of a stretched string. And you know, tell me, if you remember, for the fundamental mode of vibration, what is the value of lambda? For the fundamental mode of vibration, when the string vibrates in its fundamental mode, lambda equal to 2L, where L is the length of the string. So I can now rewrite this formula for the frequency of vibration as, you can see this is the fundamental mode of vibration. And at that time, wavelength equal to 2L. So I have F equal to 1 over 2L square root of T over mu. Tell me, what does this F represent? Because we replace this lambda by 2L, this is the frequency of the fundamental mode. Frequency of the string when it vibrates in one segment. So the frequency of the fundamental mode of vibration of a stretched string is 1 over 2L square root T over mu. Now, this equation can now be used to describe the laws of transverse vibrations of a string. Let's do that. Now, first law says the the fundamental frequency of vibration of a stretched string is inversely proportional to the length. Is that right? The length is on the denominator. If all these other quantities are kept constant, in other words, the tension and the mass per unit length are constant, then the frequency is inversely proportional to the length. It means as the length of the string becomes shorter and shorter, the frequency becomes higher and higher. Is that right? Yes. If you look inside your piano, the highest frequency is produced by the shortest wire, and the lowest frequency is produced by the longest wire. Frequency of the fundamental mode of vibration is inversely proportional to the length of the string when the tension and the linear density are constant. The second law says, for a given length, if length and the value of mu, well, mu actually describes the thickness of the wire. If length and mu are kept constant, then the frequency is directly proportional to the square root of the tension. And that is the second law. Third law is the frequency is inversely proportional to the square root of mu. That means a thicker wire will produce a lower frequency. So these are the three statements of the laws of transverse vibrations of a string. You must be familiar with those three laws. The fundamental frequency of a stretched string is, you know this, F1 equal to 1 over 2L square root T over mu. And when the string vibrates in its second harmonic, look at this, lambda will be equal to L. So what will be the equation for that then? F2 equal to 1 over L times square root T over mu. And this is equal to actually twice the fundamental. You know that. Similarly, the frequency of the third harmonic will be 3 times the fundamental. Well, all these information we already know. All right. The fourth harmonic. Now, the higher harmonics are also called overtones. Overtones. The second harmonic is called the first overtone. The third harmonic is called the second overtone, and so on. So, overtones are higher harmonics. Let's now solve a couple of problems. A string fixed at both ends is 3 meters long. It resonates in its second harmonic at a frequency of 60 Hertz. 60 Hertz is the frequency of the second harmonic. What is the speed of transverse waves on the string? Well, let's pick out our data. L equal to 3 meters. The frequency of the second harmonic, watch that, F2 equal to 60 Hertz. The string vibrating in its second harmonic vibrates in 2 loops, like this. That means since the length of 2 loops equal to 1 wavelength, length 3 meters gives you a measure of the wavelength of that wave. So what is the wavelength of the wave here? The wavelength of the wave equal to the length of the string, which is therefore 3 meters. And now, what are we supposed to find? Speed of the transverse wave. Well, speed equal to V equal to F lambda. We know the frequency of the second harmonic. We know the wavelength of the second harmonic. Therefore, we can calculate the wave speed. So, wavelength equal to 3 meters, V equal to F lambda, that will be 60 Hertz times 3 meters, that is 180 meter per second is the wave speed. Alright, another one. The wave function yxt for a certain standing wave on a string fixed at both ends is given by this. Now, do you remember the general wave form of a stationary wave? Yes, it will be y equal to a sine kx cos omega t. You see that? A sine 2a, is that right? 2a sine kx cos omega t. You can see that is the wave function given to you. What are the speed and amplitude of the two waves that result in the standing wave? What is the distance between successive nodes on the string? Remember, the distance between successive nodes is equal to half of the wavelength. So if you know the wavelength, then you know the distance between successive nodes. What is the shortest possible length of the string? Well, the shortest possible length of the string will be the distance between two nodes, because that is the lowest mode of vibration. Okay, let's do this problem. The general equation for a standing wave on a string is y equal to 2a sine kx cos omega t. That means compare this with the given equation. 2a equal to 0.05 meter, k equal to 2.5, is that right? Kx, 2.5x. K equal to 2.5, omega equal to 500. You can see how the wealth of information contained in the equation of the wave. A is the amplitude, k equal to 2 pi by lambda is the wave number, and omega equal to 2 pi f. Alright, let's now pick the values and do this problem. Comparing the general equation to the equation of the wave, we have 2a equal to 0.05 meter. That gives you A, the amplitude of each wave is 0.025 meter. You got k equal to 2.5, but k is 2 pi by lambda. So 2 pi by lambda equal to 2.5. We can obtain wavelength right away from there. So wavelength lambda equal to 2 pi divided by 2.5, and that will be, well, I didn't calculate that. You can calculate that on your own. What is that 2 pi divided by 2.5? And 2 pi f omega, this quantity is omega, which is 2 pi f equal to 500. Therefore, f equal to 500 divided by 2 pi. Well, I left these without calculating because I'm going to use them to find this quantity. What do I need to find? Speed. How do I find the speed? V equal to f lambda. So V equal to f lambda. F is 500 over 2 pi. Lambda is 2 pi divided by 2.5. There you are. And you know why I did not calculate those values. You can see 2 pi and 2 pi will cancel in both cases. Therefore, V equal to 500 divided by 2.5. That is 200 meter per second. Alright, let's now go and do the B part. What is the distance between successive nodes on the string? Well, what did I say the distance between two successive nodes is? The distance between two successive nodes is half of a wavelength. Distance between successive nodes is 1/2 of the wavelength. Now, this is the distance between two successive nodes. That is a node, that is a node, and that distance is half a wavelength. And wavelength, you know, and therefore we know that distance. Lambda equal to 2 pi divided by 2.5, therefore lambda by 2 equal to 2 pi divided by 5. And the distance between successive nodes is therefore 2 pi divided by 5 meter. Can you answer the last part? I have actually answered that for you. What is the shortest possible length of the string? Well, this is the shortest possible length of the string, which is 2 pi divided by 5. Since the fundamental is the lowest mode of vibration, the string must have a minimum of 2 nodes when it vibrates. It cannot have anything less than that. So this is the shortest possible length of the string, which is 2 pi divided by 5, that is 1.26 meter. Okay, let's do another one. A steel wire having a mass of 5 gram and a length of 1.4 meter is fixed at both ends and has a tension of 968 Newton. Find the speed of transverse waves on the wire. Find the wavelength and frequency of the fundamental. Find the frequencies of the second and third harmonic. Well, this is old story. We have been doing problems like this. Find the speed of transverse waves on a string. What's the equation for speed of transverse waves on a stretched string? V equal to square root T over mu. Let's pick out data. Mass of the string is 0.005 kilogram, 5 gram. Length of the string is 1.4 meter. You have the length, you have the mass, you can find the mass per unit length. Is that right? Yes. The tension on the string is 968 Newton. Mass per unit length is mass of the string divided by its length. That is 0.005 kilogram divided by 1.4 meter. That is 0.0036 kilogram per meter. You now have the linear density mu, you have the tension T, we can find the speed of the wave on the string. V equal to square root of T over mu, and using the values of T and mu, we get V equal to 519 meter per second. Can you stay at this point and answer this for me? Find the wavelength and frequency of the fundamental. The fundamental. The wavelength of the fundamental is related to the length of the string. Is that right? The length of the string is equal to half of the wavelength. So if 1.4 meter is half of the wavelength, then the wavelength will be twice that. Alright, let's write down that. The wavelength of the fundamental is 2 times the length of the string. You see, this is the fundamental, the wavelength will be 2 times the fundamental, and the 2 times the length, therefore that will be 2 times 1.4 meter is 2.8 meter is the wavelength of that wave. What is the frequency of the fundamental? Frequency of the fundamental is V over lambda. V we calculated. What was the velocity we calculated? 519 meter per second. Wavelength is 2.8 meter. Therefore, the fundamental frequency is 185.35 Hertz. Alright? Once you know the fundamental, do you know the second and third harmonic? The second harmonic is 2 times the fundamental. The third harmonic is 3 times the fundamental. So F2 equal to 2 F1. which is 370.7 Hertz. F2 equal to 3 F1, which is 556 Hertz. Alright, now these kind of problems are pretty good and you must be feeling pretty comfortable doing them. Let's do one more problem before we close this lesson. The length of the B string on a certain guitar is 60 centimeter. You know that a guitar has several wires, thin wire, thick wires, and each wire you can finger it to produce different frequencies, the do, re, mi, a, b, c, and so on. Here the B string on a certain guitar wire is 60 centimeter long and its fundamental is 247 Hertz. What is the speed of transverse waves on this string? If the linear mass density of the guitar string is 0.01 gram per centimeter, what should be the tension when it is in tune? What is the meaning that a guitar wire is in tune? A guitar wire is in tune means the string that is meant to produce a certain frequency, if it doesn't produce that frequency, then the guitar is out of tune. It is useless. You see? Because a wire that is supposed to produce the frequency B, that is 247 Hertz, must produce that frequency. And what are the factors on which that depends on? The tension of the wire. So the guitar is actually tuned by tightening the wire or loosening the wire, by increasing the tension. I'm sure you have seen people doing that. They pluck the wire and they turn the screw until the frequency is the right frequency. Well, let me see if I can show you a stretched wire and how the frequency depends on the length. Well, here I have a stretched wire. It is stretched between this point and this point. And I can adjust the tension by either pulling it backward or forward. Well, this is actually pushed to the limit. Now, listen to the fundamental note when I pluck it. I can actually see it doesn't record very well, but you can see when I pluck the wire, it vibrates in one segment. Can you see that? There you are. It's vibrating in its fundamental mode, producing that frequency. This is the fundamental frequency. Now, listen, if you can, what happens when I decrease the length. If I hold this aluminum rod here, I'm decreasing the length of the vibrating string. What happens now? What is the difference in the frequency? The frequency is now higher. If I decrease it further by bringing the aluminum rod, you can see the length is now decreased. You see? It is a higher frequency. If I increase the length, the frequency decreases. There you are. So, as you increase the length of the wire, its fundamental frequency decreases, and you decrease its length, the fundamental frequency will increase. Alright. Okay, what are the given information in this problem? You are given the length of the wire, that is 0.6 meter. You are given the fundamental frequency, 247 Hertz. You are given the linear density. And now, what's the unit? It is given in gram per centimeter, 0.01 gram per centimeter. Convert that to kilogram per meter. That will be 0.001 kilogram per meter. Alright, what do we need to find first? What is the speed of transverse waves on the string? Well, to find the speed, what are the things that we need? Well, we can find the wavelength of the fundamental. Is that right? Now, how do we find the wavelength of the fundamental? Wavelength of the fundamental is related to the length of the string. You know that when a string vibrates in its fundamental mode, there are two nodes at the two fixed ends. The distance between two successive nodes is half a wavelength. So lambda 1, the wavelength of the fundamental, is 2 times the length of the wire, which is therefore 1.2 meter. The wavelength of the fundamental is 1.2 meter. The frequency of the fundamental is 247 Hertz. Alright, do we have enough information to find the wave speed? Yes. V equal to F1 lambda 1, which is 247 Hertz times 1.2 meter. That is 296.4 meter per second is the speed of transverse waves on that string. If the linear mass density is given, what should be the tension when the wire is in tune? If this wire is in tune, what is the tension on that wire? Well, how do we find the tension? We know the wave speed. We know the linear mass density. Isn't it possible to use these to find the tension? Because you know V equal to square root of T over mu. There we are. Can you solve for T from here? T will be V squared multiplied by mu. We got the value of mu. We got the value of V. Therefore, the tension must be, this is the mu value. This is the velocity, and you square it. That gives me 87.9 Newton is the tension of that string when that string is in tune. So I hope you now have a fair idea what is the meaning of tuning a musical instrument and what is the relation between the fundamental frequency and the length of the wire and so on. Now later on we will spend a few more minutes on talking about musical instruments. Then we will talk about all this one more time. Well, I'm going to close this lesson here. Please go back and do the homework. Alright, we are now nearing the almost the end of Unit 1. There are a couple more lessons left. I will see you for the next lesson a little later.